Welcome back, everyone, to the last talk of today's session. I'm happy to introduce Elena Hermans, who will talk about virtual double categories as colored boxed operads. Thank you.
Yeah, thanks. I want to start out by saying thank you for everybody for attending and for the organizers for inviting me. As you might hear, I have a bit of a cold, so I will do my best to give you some sort of a pleasant talk. And in this talk, I will try to talk to you about virtual double categories as a colored version of box operads. And you might already have heard that virtual double categories appear under many names. Most of the, probably a very well-known one is generalized multicategories and Leinster's FC multicategories in particular. And so you might ask, how am I here then with a new name, box operads, adding this to the heap? But it's definitely not my intention here to advocate that this is the best name in the game. But it's rather to emphasize that we want to point out a different point of view on how we could use virtual double categories. And this time is a sort of operatic structure. And that's why we use box operads, because in algebraic geometry, in algebraic topology, operads have a very big role. So I hope I will be able to explain this to you. So let me first start out with a bit of a roadmap. How can we contextualize or situate virtual double categories? Well, if we start out with the most simple thing, we start with monoids, well, then there are two very natural generalizations that are very well known. And the one is going to categories. Instead of having an associative multiplication, we go to a composition that is defined when the objects match up, still associative. And a different way to generalize monoids is to look at operads. Operads are spaces of operations with many inputs and a single output. And monoids only have one input and one output for its morphisms or elements. And if you sort of complete this square, you end up with what's called, in some settings, multi-categories, but it coincides with in algebraic topology is called colored operads. And I know it's a bit of a contentious name, but I will use it anyway. And the interesting thing here is that these multi-categories also generalize monoidal categories, in the sense that in a monoidal category, we can tensor both our objects and our morphisms. So to have a morphism with many inputs and one output, we can actually write it down as certain morphisms from one input to one output by tensoring its objects. And as I know, I'm quite sure many people here in double categorical world know, double categories neatly generalize these monoidal categories, where we go to sort of rectangular categorification of these one category structures. And it's here that I want to really place virtual double categories as a sort of completing this lower square, where we have sort of a two categorical structure where the two morphisms have some sort of rectangular data, and you can compose them in a sort of operatic way. And this is also where I want to really propose this new thing called box operads as some sort of, in a certain sense, a one-colored version or an uncolored version of virtual double categories. And in that sense, we could see virtual double categories as some sort of colored version of our box operads, depending on how you want to really look at it. So to give you a little bit of a history on what virtual double categories have appeared, it's actually started in 1971 by Bironi, where he introduced them as multi-categories over a monad. And then Leinster, when he did his review in 2004, he gave this monad a name called the free category monad, and he's called them FC multi-categories. Not much later, Dawson, Paré, and Pronk called them lax double categories because they have this double category of flavor with some laxness to it. And then Critwell and Shulman settled on virtual double categories. And I think this is for now a bit accepted name. And recently they have also appeared in papers under with an adaptation called augmented virtual double categories of Koudenberg. And then now my collaborators Wendy Lowen and Huang Din Van and I, we propose this box operatic setting sort of influenced by the applications we are aiming at. And as I told you in the beginning, I want to sort of propose a different point of view in the following sense. If we look at the easy case categories, we could perhaps use it in two, not necessarily orthogonal ways, is either we can look at them as some objects of study. We're interested in the category of groups, of abelian groups, the category of simplicial sets, and we're interested in their properties. But in another way, you could say, okay, we can use a category as something that encodes algebras or modules over it. So for example, the simplex category encodes simplicial sets. A ring can encode its modules. A K-algebra can encode its modules. So it sort of captures maybe the calculus of this category of study through the category that encodes it. And this point of view is really followed when the renaissance of operads came about, when you have these operads appearing in algebraic topology. Well, you have the operad ASOC encoding associative algebras. You have the symmetric operad Lie encoding Lie algebras. And you, for example, have this operad op, which encodes in itself non-symmetric operads themselves. So here we really are interested in the calculus that underlies this, and then they should encode all the good properties of the algebras they encode. And in a similar way, we could say, okay, if we look at a monoidal category as a multi-category, well, it's encoded, for example, the monoidal category of modules over a ring and its tensor product. We could say, okay, we're not really interested in what it encodes, but we're more interested in the formal properties of this category itself. And as far as I understand, if you look at virtual double categories, most of the examples that we're working with, for example, a very well-known one is the functors, they fall into this first category, where, for example, we're looking at the double category or virtual double category of functors, of discrete fibrations, of bimodules over in some monoidal category, symmetric monoidal category V. And of course, we're also interested in them. And specifically, we will be interested in these spans enriched over a monoidal category V. Just to point out, we're really interested in these very non-Cartesian monoidal categories that we want to enrich over, because in algebraic topology and geometry, we're interested in the linear world and not very much in the Cartesian product. And so what is my aim here to point all of this out? To point out is that the applications we're looking for, the way we want to use virtual double categories as box operads, is we are looking at these new examples that we've defined called lax with some index u, colax with some index u, and press with an index u. And they will encode categories algebras, and this will be lax functors over the small category u, a one category, into the two category of linear categories. This colax then is colax functors of this kind, and then you have press. Press are pseudo functors of this kind, and these are really the objects that we're interested in, because pseudo functors of this specific kind, they are called in algebraic geometry prestacks. And prestacks appear in this algebraic geometric world because if you are starting to do a deformation theory of schemes, then it turns out that prestacks can encode such non-commutative deformations. And these prestacks for us live both in the moduli space theory, but also in a sort of non-commutative algebraic geometric world. And it's very interesting because that's also sort of our main motivation for developing this whole box operatic framework is we want to encode prestacks via these colored box operads. And our aim is to study their deformation and homotopy theory almost purely via these sort of two categorical or double categorical diagrams, as I will hope to explain to you in the rest of this talk. So let me maybe, before we go that big up until these very applications, let maybe give you an intuition of how to think about box operads and colored box operads. So if I start with the baby case, if we're working with operads, then you would say, okay, we have these operations with many inputs, and we can graph them or compose them on top of a single one here and make a new operation out of it. This is sort of the composition, and it works in a sort of operatic associative way. If we then think about multi-categories, it's exactly the same. We're just starting to color the inputs and outputs. So they have an objects, they take value in objects, and then we can only compose if these colors match up. Now, a monoidal category, we could also draw in a similar way, where we have this categorical composition of one arrows, but we also have this tensor product, which allows us to sort of tensor up two arrows with each one input to an arrow with also one input and one output, but we have tensored up their object, their domain and codomain. And in this way, we can build from a monoidal category a multi-category. Now, what are box operads? So to us, we're sort of a rectangular version or a boxy version of operads. So if we would do this intuitively, we would draw it as follows. Suppose we have these operations, which now has both inputs at the top, but also on their sides. And we're able to stack them on top of each other with one at the bottom and then a whole row, but they should all neatly have the same amount of in and outputs on the sides. Then we can neatly compose them by erasing this middle part to get a new box. And this is, if you know virtual double categories, it's sort of a colored version of this, where we both color the objects, its horizontal morphisms, its vertical morphisms, and then you have these two cells in the middle that we can compose. For maybe the real experts in virtual double categories, you might think, normally we also compose the side arrows. I will sort of sweep this under the carpet for now, because we sort of take the free category on the vertical arrows, but I will not get into that detail. And then double categories, as we know it, are sort of can also be drawn in this colored version, where we have both a vertical composition of arrows as a horizontal composition. And so every double category can induce a virtual double category by first composing the top layer and then composing vertically the two on top. So that's sort of the intuitive definition of what is box operads and colored box operads. Now, I know we're mathematicians, so we would like something very precise to be able to tick off some of the boxes that our questions might reach. So I will give you a very explicit definition of what is a box operad enriched over some symmetric monoidal category V. So for example, what does it consist of? Well, first we take for a collection of objects in V that are indexed by 3 natural numbers, and every element in there represents a box which has Q vertical inputs, a single vertical output, and we have P inputs on the left and R outputs on the right. As you see, this is a bit of a choice where I say this is input, this is output. You can also turn it around, but let's go for one choice for the moment, just intuitively. Then the second part is we have this collection of objects, and then we sort of have a composition. And how does the composition work? Well, they need to match up here in the middle. This has n inputs, so we can put n boxes on top of it. And then we add up all the numbers on the sides and erase what's in the middle. And this is what we call the composites. And as you know, compositions, we often want a unit for it, and the unit will be placed in the array 0, 1, 0. So if we would now make this purely a categorical definition, we would say, okay, we have a composition map we have these objects, we have this composition map with the monoidal product from this monoidal product to this outside box with this array, and we have a map from the monoidal unit into the B's with array 0, 1, 0. Now, to have associativity, we should also, we have to express some sort of associativity, and it can be done by saying, okay, if we have 3 layers of boxes stacked, we could say first we compose the top 2 layers, or we could say we could have composed the bottom layers and then the top layer, the upper layer on top. And this should be equivalent, it should be the same for a general box operand. So that's the associativity condition, and the unit condition is sort of the same, but then you place units on top, should do nothing, or we could place 1 unit at the bottom. This should also not do anything. Sort of an interesting thing that I want to point out is that we draw these units, which is already 0, 1, 0, 1, 0. We draw these sides. We should have drawn it as a thin line. But because we want to keep a rectangular drawing, we sort of make it thick and write these equality signs whenever there's a 0 popping up. And this has sort of interesting consequences. And one peculiar degeneracy that already Leinster pointed out in his paper is if I would take a composition for the n is 0, if we would draw this map, we would still have this starting object, which has boxes of the size P0 R. So you see here as well, we don't draw it as a rectangle, we draw it as a square with this equality sign. Well, the composition map sort of adds on this sort of vertical degeneracies on top. You add on P0 vertical morphisms on each side. And this is necessary to get to actually fully express the associativity condition when we're working, when we're allowing zero array inputs in there. So this is sort of, we have these horizontal generous units using the unit that's out there, but these vertical units of double categories, they don't really exist in this virtual double category world, but we can still see these maps that they induce. Okay. So this is one sort of peculiarity that you want to see. And then there is this one thing that is our sort of key observation for box operads. And it's that we can embed operads as what's called thin box operads. And these thin cells will sort of be the key to the whole theory that we will develop later on. So I want to really press on it. So we have this embedding, and how does it work? Well, what is a thin box? It's simply a box where the sides are 0. It's sort of these boxes that should actually be lines. And the reason why is because, well, if we have this operation of operads, we could just make it into a thin box by taking the sides to be 0. And then the whole composition of operads works perfectly well because these zeros don't really influence this box operatic composition. Now, a very important part here is that for operads, you've probably seen them defined not using the full composition, but using a partial composition. And the same you could not do for box operads. We do still have certain partial compositions, namely if we stack on top of a whatever box, a thin box, we can always do a partial composition by filling in these blanks with the unit. However, if I do this with a non-thin box on top, we have these open spaces that we're unable to fill canonically. So this, the result of this is that box operads will be a very non-quadratic theory, while operads themselves are very quadratic in their definition, similar to categories. So this prevents us to redefine the full composition of box operads as some sort of iterated partial composition. Okay, so this is sort of the first part of the thing before I will go into the higher theory of box operads that we developed to do our application. Maybe there are already questions. Or you can put them in the chat and then I will read them when I'm presenting. Okay, so what is the floor plan to where we really want to reach? And it has a couple of chambers that sort of are independent, but each part of it, you need to get to the end results. And we want to sort of do a deformation theory from an homotype theory of these lax functors of this shape. So I'm not presenting this for any two categories of lax functors, but only where this is a small one category and this is the two category of linear categories. So the first thing I want to show is that actually box operads are monoids, but they're not in a monoidal category, but in what's called a skew monoidal category. And it's kind of obvious, but we will need it, is, well, we have to define for a skew monoidal category also some sort of a composite, which is the box composites. And the box composites takes these collections indexed by 3 natural numbers, and you take 2 of them and make a new one. So if I would take with these 2 modules, I take the box composites and I evaluate it in P, Q, and R. Well, I just divide it up in two rows where the bottom row is always M and the top row will always be N. And then, of course, we need some compatibility between these sides. So we take this co-product where we say this should add up to that. These Q's should add up to Q, and these P and R should add up to R here. So this is a neatly defined functor at least. And we showed that this is in fact a skew monoidal category. What does it mean, a skew? Well, first of all, to also say that the monoidal unit of V is placed in array 0, 1, 0. I think you probably know why that's done. Okay, so suppose what is the difference with skew monoidal and normal monoidal? Well, if we look at its associator in the monoidal category, this should have been a natural isomorphism. In the skew case, this is directed, and we can actually draw why this is true. If we take an element in the top iterated box composite, we see that either we take first we first split the lower level up into two layers of boxes, and then we add on top a box at the top. Of course, we can also reinterpret this here, and this lives in this lower iteration of box composites. So this is a neat embedding. However, I can draw a box that's living in here, but that won't live in here. I'm sorry, I can draw a stacking of boxes that lives in here, but not in there. For example, I can do the following. This one here is, well, first I have this NK living both in this box composite because I can split them up individually themselves. And then I can put this on top of an M, which means it lives in there. However, what can I not do? I cannot switch anymore. I can't first compose the N and the M's because they together do not form a neat stacking of boxes. So here we run into an issue, and it has some formal property, it has some formal problems later on. For example, when we're looking at left or right modules over our monoids in a skew monoidal category, the ones have, I think the right ones have a very neatly defined theory. The left ones will have a lot of problems. So what did I show? Box operads are exactly monoids in the skew monoidal category, meaning the composition map can simply be described as this map from B, box composite B to B, and the unit is, of course, from the monoidal unit to B. So this is one result that is sort of important to us. And a second result is, well, we have them as monoids, but we also want them sort of as what is the free box operads? What is the calculus underlying virtual double categories or box operads? And so what did we do? We made a symmetric colored operad whose algebras are exactly box operads. And the reason why we did this, and that's sort of the nice salient feature of it, is once we have this, we defined for every box operad a totalization which carries an L infinity structure. So this generalizes what's happening in the operatic case, where every totalization of an operad has a Lie structure, and in our case, we will have an L infinity structure. And the nice thing is that this will be can be fully explained with these two categorical diagrams. So first we start out with what is this box, this symmetric colored operad, and it's governed by what's called stackings. Well, what is to us a stacking? A stacking takes a sequence of boxes with certain arities, and it stacks them to form a new box. And I know this is kind of vague, but let me give you a couple of examples. For example, this to us is a stacking, and the second part is also a stacking. So here we have a stacking of 10 boxes, and they form a new neatly box where, of course, I have now a bit omitted the sides, but I drew them in a neat way. But in the second part, we also have this stacking where we stacked on top, for example, here, this thin box 4, and you might see, okay, this looks like a stacking, but why do we allow this? And again, this is because if it's a partial stacking, we could fill this neatly up using the units of our box operads. So this to us is all the allowable stackings of boxes, and I think we gave a very combinatorial description of this. So what does then this colored symmetric operad that we call box op? look like? Well, first it's objects or it's colors. Of course, we take triplets of natural numbers. And then the question is, what are the elements of this space that takes these arrays into the array PQR? Well, it's the set of all stackings of boxes of this arrays into a box of the array PQR. Now, that's just a set. For an operand, we need a composition. And in the case of norm plane operads, this happens with trees and substitution of a tree in a vertex. So in our case, we will work with what's called substitution of a box by a stacking. And I think in your you can intuitively see how that would happen. So let me give you a very concrete example. We have this stacking of boxes, of 5 boxes, and I want to compose it at the second component by this other stacking of boxes. As you see, they have the right arrays. It has array 1, 2, 1, so 1, 2, 1. And so what do? We take the first box, we have to enlarge it a little bit, and then we place the second box in it. Now you need to sort of reorder the numbering. So what we get is that it has a unique composition where we simply place this box in the middle of that box and reorder it. So this is, each box sits on a single box. So that's indeed a very important property. That's a question from in the chat. The rule of stacking is each box sits on a single box. Yes, that's right. So that's why we call it operads and not, for example, props or properads, is we only allow them to have a single output at the bottom. This will make the theory very contained, and it will prevent problems like the spin wheel, which is only possible if we have multiple outputs at the bottom. So this makes it into a very neatly defined theory, and that's sometimes the game of operads and generalized operads. It's finding the right restrictions and the right framework for your application. That's at least my point of view on that. Okay, and then the proposition is, well, every box operand will indeed be an algebra over this and will be exactly the same category of algebras. Now, now what did we show? Well, we showed that we have a morphism that will go from the operand L infinity to, well, this is a symmetric colored operand. We want to make it uncolored, so you sort of have to make a subtle totalization, which I won't bother you with. But what is nice is that it means we need to now say where every bracket, what it will look like. How will a bracket look like in this set of stackings? Well, if we look at the operatic case, it will actually be this first set. It will be all summation over all partial compositions of 2 thin boxes or of 2 elements in your operads. This is what's called the Gerstenhaber bracket. Now, in our case, we want to do more. Now, this completely forgets about all the non-thin boxes. So we added another component. And this is, for example, we can still do partial composition where the top box needs to be a thin box. So this we allow, and we sum over all of these. But then we also want to be able to do a thin box at the bottom and a non-thin box at the top. Somehow that's not possible. So what do? We add up all the stackings, which exists out of exactly 1 thin box at the bottom and all non-thin boxes at the top. To make this work, we also need to add a topological condition, and this topological condition states that the horizontal composition in that direction should be connected. That's the only condition we add. And it's sort of very fascinating that this calculus of stackings always induces this L infinity structure that always exists on there. So as a result, every box operand its totalization induces an L infinity algebra. And the reason why this is necessary is we need these both approaches to talk about what's called a Koszul duality for box operands. Or as you can think about a Koszul duality for virtual double categories. What do you need? You need this L infinity structure. You need to make a bar and cobar construction using the free box operand construction. You need that this bar cobar will be exactly the differential will be equivalent to this L infinity structure. And then the question is, okay, with Koszul duality, we can start with a box operads and try to make a cofibrant replacement using bar-cobar. And then the question is, okay, how computable is this? And you can compute it using a Koszul complex, which is based on modules over the box operad as a monoid. So all these three components are necessary to make a Koszul duality. And the reason why we do this is because we want to, as a next step, we want to define a colored box operad lax that encodes our functors. And then we apply Koszul duality to it to find a minimal model, which we will call lax infinity, which is sort of lax functors up to homotopy in a suitable sense, in the DG sense. So that's our sort of approach. So let me now go into this chamber and tell you a bit about what this place looks like. So the box operad lax, let's start with the uncolored version. If you don't understand any of the algebraic geometry topology words I used, we can just try to understand what this cute little object looks like. Well, we start with three generators. A first sort of multiplication that is thin and two inputs at the top. Then we have this F, which has already 1, 1, 1. So this encodes the local categorical structure. And this will encode the functors between the categories. And then we need to sort of interpret how we will do the lax structure, which in our case translates into a natural transformation. And this will be of the shape with 2 here, 0 there, and 1 here. Oh, I see that my computer is not plugged in. Yeah, okay. Voila. So what do we see? These three elements should encode the calculus of our lax prestacks or these lax functors. So now we have to apply some relations to it. And the first one is simply associativity as we know it. So we have this associativity of the multiplication. And then the second thing is a more interesting one where we see, okay, what does a functor do? It's if you compose two morphisms after you apply the functor, it's the same as first composing the morphisms and then applying the functor. So this is a quadratic relation, and this is a cubic relation. That's why plain operatic theory doesn't really work well, because it always restricts to a quadratic setup. Now, what is the third thing we want to encode? This should be a natural transformation, which means that it should sort of commute with the two functors it goes between. And so what we say is after we compose this element in the category, after twice applying this functor, it should be the same as first composing this element with once applying the functor here. So this is sort of horizontal commutativity, and this is some sort of vertical commutativity going on. And then you have this condition, which is called the co-cycle condition for prestacks. And as a matter of fact, it's simply the translation of the pentagon identity for lax functors. So we here encode locally categories, functors, natural transformations that that satisfy the pentagon identity. That's how we encoded this using, in the language of double categories, a virtual double category. Now, the nice thing is, as you might know from monoidal categories, you have this MacLane coherence theorem. So you might also ask, can we define these lax absolutely without giving generators and relations? So we did this, we computed what it looks like, and it has sort of, you can compute its dimensions, and it depends on what is called the partitions of the number P into R non-empty partitions for these numbers when it's equal to 1, and otherwise it's going to be 0. So, okay, it's a bit abstract, so let me maybe break this up into important parts. The first part is, as long as the left number of inputs is smaller than the right number of outputs, it's always 0. It's impossible with this M, F, and C of disparity to make, for example, a box of the shape 2, 3, 3. That's impossible. So these will always be 0. These fit into this side. Now, what else? If we look for example, when P and R are 0, so P and R are 0, Q is bigger or equal to 1, then we will always have a single partition, so it will be one-dimensional. Or, differently put, the thin part of our box operate lax will be the operate ASOC, as we sort of wanted. And in the classical framework of ASOC, you call this element MQ. It's a unique composite of Q minus 1 times compositions of M. And then you have this third component, which says, okay, if this R is 1, so this is always 1, and some conditions here, then this will always be one-dimensional. And that's some sort of coherence result in the following sense. For example, this stacking we can compose, and it will live in the place 3, 1, 1. But we can write it in many different ways. So any box of the array 3, 1, 1 will all be the same in lax using these relations. For example, what could we do here? Here's a C into Fs. Here's an M at the bottom. We could have applied the natural transformation relation and switch these around. We could have, then we're here, we could say, here's a C, the F, the C, and we have a multiplication underneath it. Then the co-cycle condition says that we can take this down. So we could do this. And you can see here, these vertical degeneracies play a role. They are very necessary for our box operands. What can we do now here? We can now place the C and the F back. For example, we can switch them back there. And then we could say, okay, now the C and the F here are down. We could also switch them back here. So anyway, you can draw a stacking of boxes of M, F, and C that has array 3, 1, 1. They all have a sequence of equalities towards each other. That's sort of the coherence result. But it is important to note, as soon as this R is larger, then there will be more options. For example, if we take the box 3, 0, 2, this will, for example, this lives in there, the C stacked on top of the S, but we could have also done the vertical degeneracy on the C, and they both live in there without being equal. And this is sort of all expressible, of course, in the categorical language of lax functors, where we do not expect these two maps to be actually the same. So to us, this really governs the calculus underlying lax functors of our setup. And then, as I've been speaking about colored box operands, well, we actually wanna, if I take an algebra of this previous lax functor, we won't get actually lax functors of the small category U, but over the 1 point category with one morphism here, but we want to do it over a given small category U, and that's why we need to do some colorings. And the colorings is done as follows. We still have 3 collections of elements, but now the first multiplication is indexed by the objects U over small category U. So for every object U, we have an associative multiplication, which is a category. And then for every morphism in U, we have one FU, which would be the functor from this category in U to the category in V. And it is on the side, it is colored by the morphism small u. And then for the natural transformation or the lax part of it, we take 2 composable morphisms in U, and then this C, which we also call sometimes twists, it goes between this functor V after U applied and the functor F1 of VU. And here, of course, you see we have 3 objects at play and 2 morphisms of the category U. Okay, so just to point out, there are no the horizontal morphisms are fully determined by the objects of U, right? There are not 2 morphisms between U. There's only a single one. There are many vertical morphisms between 2 objects. Okay, and then the relations simply express the same idea. You have, for example, here you have this FU for a morphism U here in U. Then we first apply the FUs here. You then apply the multiplication in V, and it should commute with first applying the multiplication in U and then the F of U. So you need to sort of take these into account. It's a sort of subtler version of lax without colors. And the same here, we apply two morphisms UV, we take FU, FV, we take these twists or this C in between it. And then as you notice, if we switch these around, you go from FU, FV to FVU. So these before were the same element, and now they're actually three different elements. And the same happens if we do the co-cycle condition where you take three composable morphisms in our small category U, and they sort of need to work well. And this is maybe more well known as the pentagon identity. In some, maybe you can see it more clearly there. Okay, and then I guess the big question now is, how do we define an algebra over such a colored box operads? And the algebra is, well, in this here, I will use what we've seen in the first class, namely a virtual double category that we're interested in as a category itself, as a virtual double category itself. And what we define is an algebra over a colored box operad is exactly the, well, this category is the category of virtual double category functors between V and this virtual double category of V of spans enriched over V. Reason why we take this is, well, if we look at it in a bit detail, elements in here are sets. So every object color in here, of course, selects one set. Then you have that the vertical morphisms are functions. So every vertical morphism here selects a function between objects. And then what are spans? They're sort of the underlying thing of a category. A category is an enriched span with a multiplication. So we take here, every vertical morphism here is sent to a span enriched over V between its two sets. And then what's then the two morphisms? The two morphisms are the morphisms of V spans, which is exactly what, in fact, a functor underlies. It's a morphism of V spans that satisfies certain conditions. So what is for us an algebra? It's simply a morphism or a virtual double category functor between them. And then we showed that indeed category of algebras is exactly the category of lax functors from a small category U to the category, the two category of linear, of the two category of V categories, V functors and V natural transformations. And this sort of finishes what we want to do, because what we then did is we resolved this category, which is now a bit too much to go into, but the resolving we did is we computed its Koszul complex, and then we used the cobar construction to make lax infinity. And then we naturally get a deformation homomorphic theory, which is sort of work in process at the moment. So if you have want any details, we have these two preprints out called box operads and the higher Gerstenhaber braces, which is the first part. And then in this, we develop in the second one, the Koszul duality for box operads via a minimal model for lax prestacks. I can stop here. I can explain the L infinity structure more, but maybe it's a cute proof, but maybe it's more interesting first if there are questions. So thanks.
Thank you for your talk. So if you have any questions, please raise your hand or just unmute. I can see that Nathaniel has already a question, so please go ahead.
Hi, thanks for the talk. I was wondering if you could clarify a bit this remark you made that there's a small difference between box operads and virtual double categories. So
yeah. Well, let me maybe. Oops. No, I don't want to do that. There we go. If we go to this definition of box operads here, well, in virtual double categories, you don't really. Oh, that's I don't want to draw. In virtual double categories, you don't really take a P simplex here. you would just take one morphism in one vertical morphism, and when you compose them, you simply demand that the virtual double category has already in itself a composition of vertical morphisms. So what did we do here? We sort of said, okay, if we take here just a set of what our vertical morphism should be, we take the free category on top of it, and then simply composing these simplicious is simply concatenations. And that's how the composition works in our setup, is that, for example, here, this P plus P0 is simply the concatenation of a P simplex plus a P0 simplex. Of course, if we get out of this uncolored framework, we go to the colored, I think there is a possibility that we could just use a definition of virtual double categories and use this as the underlying calculus that sort of governs these virtual double categories. If that answers your question.
Yeah, thank you.
We have time for more questions.
I can also explain to an infinity structure that's of interest.
Nathaniel has another question.
Shoot.
Maybe I'll ask one more quick question. So on one of your final slides, when you were looking at the algebras for the colored box operads, yeah, maybe if you go to it first, so I remind myself slightly earlier. Yeah, this slide. So there's a relationship in the paper of Crutwell and Schulman, where they show a nice relationship between lax functors into span and normal lax functors into monads in span.
Oof, okay.
I'm wondering if this is at all related to the relationship here.
So it's lax functors from what into span?
So they show that if you've got lax functors between virtual double categories, then by applying the monads and bimodules construction, you get an equivalence between, say, lax functors from A to B and normal lax functors from A into mod B. And it's not quite the same as on your slide, but has a similar sort of flavor, because if you look at the monads in span, you get the category. So I was wondering, is there any relationship?
Well, I should look into it. I don't. That's definitely has not been our point of view, I think. Let me think if there is something sensible to say about it. I will look into it, because there are these many rewrites that you can do. For example, the Groton deconstruction has also been applied to these lax functors to get fibered categories, which is somehow different, but I don't know if that has this flavor, for example, but it's something I should look into.
On this slide, you talk about spans enriched in V. What do you mean by that exactly?
So in the linear world, we're really enriched. We're really interested in this category of K modules, which is non-Cartesian tensor products. So a way to do K-linear categories and stuff, you say, okay, what is for us a span? It's not anymore an object with two morphisms out of it, but it's simply a collection of objects in V that are indexed by a set of domains and set of codomains. And then an algebra is a category can in this way be defined. So our point of view on spans is also something called bi-co-modules inside a monoidal category. So yeah, that's our point of view. So if you want to see different types of algebras, I could have replaced, of course, this virtual double category, but whatever objects you're actually mostly interested in. If you're more interested in bimodules, sort of lax functors of categorical bimodules, then you can change this around. But the main point is that the calculus here won't change much.
This is related to Marcelo Aguiar's work on bimodules and things like this in a monoidal category. Marcelo Aguiar.
Yeah, exactly. So
Right,
this is definitely the work of Aguiar is definitely the way I look at enriched category theory. And that's also, yeah, so I definitely consider this a bicomodule idea.
Okay.
Where we try to avoid as much as you can any Cartesian properties or things like this. Yeah.
Okay, great. I'm not sure if Nathaniel has a third question or if he's
Or
hand.
is
Right.
No. Yeah. Yeah. If there are no more questions, I can give yeah, either I stop or I can fill up the 9 minutes if that's fine for you.
Well, let's at least thank you again for the lovely talk.
Thanks.
And I guess we can officially finish there, but sure, if you would like to say something more, that's also perfectly fine.
Yeah, maybe just the one thing. Oh, I didn't want to do that. One thing that is sort of neat is the following, that this L-infinity structure that we came up with, it fully depends on this this calculus of stackings of boxes, or this calculus of double categorical diagrams. And you can sort of, we have these 4 cases, and this is sort of how you can draw all of these relations. Where, so if you're more interested into how it looks like, I wouldn't be too scared. And if you're interested in how these calculi can give us sort of Lie structures, I think if you want to understand this whole thing more, then I invite you to come look at our paper and see how these combinatorial things give you higher structure. So I want to end then there. Yeah. Well.
Great. Thank you.